In this week's video, we're going to be covering generating functions. This includes moment generating functions, cumulant generating functions, as well as linear functions. So for those of you preparing for the CS1 exam, this video is for you. Let's begin with moment generating functions. A moment generating function is used to generate the moments of a random variable about the origin. Now, what exactly are moments? Moments are basically the expectation of different powers of a random variable. For example, the expectation of x, the expectation of x squared, etc. MGFs are extremely important in probability, statistics, and actuarial science. This is because they help to calculate the moments easily, they help in identifying the distribution, and they're also useful in simplifying many probability problems. The MGF of a random variable is represented by m of t, and the formula used to calculate this is given by m of t is equal to the expectation of exponent to the power tx. Here, capital X represents the random variable, t is a parameter, e is the exponential constant, and the expectation means the weighted average in probability. The idea is that after expanding the exponential term, the moments automatically appear inside the expression. That's why it's called a moment generating function. The MGF doesn't exist for all distributions. This is because for some distributions, the expectation becomes infinite or cannot be evaluated. Now, let's discuss some of the important basic properties of MGFs. Starting with the first property, the value of MGF at t equal to 0 is 1. We start by writing our function and putting 0 in place of t. The MGF is given by the expectation of e to the power tx. Exponent to the power 0 is essentially equal to 1. This gives us the expectation of 1, which will be equal to 1, thus proving that the MGF at t is equal to 0 is equal to 1. We move on to the second property. For a discrete random variable x, the expectation is calculated using the summation. Therefore, the MGF becomes summation of exponent to the power tx times the probability of x. This is because we take each value and multiply it by its probability. Let's understand this with an example. Suppose the probability of the random variable x is equal to 1 is given by 0.3, and the probability of x is equal to 2 is given by 0.7. Find the MGF. Using the formula above, we get m of t is equal to e to the power t into 1 into the probability of the random variable being 1. To this, we add e to the power t into 2 into 0.7. This gives us Now, let's verify if this is correct. We put 0 in place of t, which gives us 0.3 plus 0.7, which is equal to 1. Now, let's look at the MGF for continuous random variables. If x is continuous, its expectation is calculated using integration. So, the MGF becomes integral from minus infinity to infinity, exponent to the power tx into the PDF of the distribution. Let's understand this with an example. Suppose a function is given by 2x, such that x is between 0 and 1. Using the formula, we get this time, if we wish to verify the solution, we directly put 0 in place of t and then integrate it. Let's learn how MGFs are actually used to find moments. There are mainly two methods, differentiation method and series expansion method. Differentiation method is the standard and most commonly used one. The basic idea is that we find the MGF, then we differentiate it with respect to t. To find the rth moment, we differentiate r times. After differentiating, we put t is equal to 0. The value obtained is the rth raw moment. And the general formula is given by. Let's understand this with an example. Let the MGF be equal to exponent to the power 2t plus 5. Find the first and the second raw moments. Also find the variance. So, to find the first raw moment, we take the first derivative of the MGF and put 0 in place of t. To find the second raw moment, the process is the same except we differentiate twice. Let's solve this. This gives us the first raw moment, the second raw moment, as well as the variance. Next, let's discuss the series expansion method. Sometimes differentiating the MGF repeatedly becomes too long or difficult. Therefore, series expansion is done. Let's understand the steps for this. We start by identifying our MGF. Then we expand it into powers of t. This can be done using the series which is the most appropriate in the question. Then we compare it with the standard expansion and identify the moments by comparing them with the coefficients. As we know, MGF is expectation of exponent to the power tx. The series expansion for exponent to the power tx is given by 1 plus tx plus t square upon 2 factorial into x square and so on. The next step is to take the expectation. This gives us the standard expansion. To find the expectation of the random variable x to the power r, we look at the coefficient of t to the power r upon r factorial. Let's understand this with an example. The example says, let the MGF be equal to 1 minus 2t to the power minus 1. Find e of x and e of x square. Here, r is given by 2t. So, Substituting that in the above formula, we get Now, we compare this with the standard MGF expansion. This right here is the standard expansion. So, when we arrange this statement in the above order, we get Next, let's talk about the uniqueness property of MGFs. The uniqueness property states that every valid MGF corresponds to one and only one probability distribution. In other words, an MGF uniquely identifies a distribution. This means that if two random variables have exactly the same MGF, then they must have exactly the same probability distribution. So, matching MGFs imply matching distributions. The uniqueness property allows us to identify unknown distributions simply by comparing its MGFs with the standard MGFs. Now, let's derive the MGFs for standard discrete distributions. As covered above, for discrete random variables, the MGF is defined as For a discrete uniform distribution, the probability mass function is given by 1 upon k. For such a distribution, the value of x begins from 1 and goes all the way up to a certain number k. Therefore, the summation will take place over the range of x, which is from 1 to k. Let's bring out the constant term. This represents the sum of a geometric series with a finite number of terms. Therefore, we use the sum of GP formula here. Here, A, which is the first term, is e to the power t. R, which is the common ratio, is also equal to e to the power t. And n, which is the number of terms, is equal to k. Inputting these values in the formula, we get This gives us the MGF for the discrete uniform distribution. Let's move on to the binomial distribution. The MGF is given by the summation of e to the power tx times the probability mass function. On observing closely, this result matches the binomial theorem. Binomial theorem is given by a plus b to the power n is equal to the summation of ncx into a to the power x into b to the power n minus x, ranging from x is equal to 0 to n. Here A is equal to P into e to the power t and B is equal to Q. So, on inputting these terms on the right hand side, we get this gives us the MGF as Next, let's talk about the Bernoulli distribution. As covered earlier in the previous videos, Bernoulli distribution is a special case of the binomial distribution with n is equal to 1. Therefore, the MGF of the Bernoulli distribution is obtained by putting n is equal to 1 in the MGF of the binomial distribution. Next, we have the derivation of the MGF for the negative binomial distribution type 1. We start by representing the MGF Now, to the power of the exponent, we add and subtract t into k. Then we take out the constant terms. After this, we use the negative binomial theorem for type 1 distribution. This theorem states that 1 upon 1 minus r to the power k is equal to the summation of x minus 1 combination k minus 1 into r to the power x minus k, from x is equal to k to infinity. Here, r is given by q into e to the power t. This gives us therefore, the MGF is given by Next, let's talk about the MGF for the geometric distribution. The geometric distribution is a special case of the negative binomial distribution type 1 with k is equal to 1. Therefore, its MGF is obtained by putting k is equal to 1 in the MGF of the negative binomial distribution type 1. Let's move on to the negative binomial distribution type 2. The MGF is Next, we take the constant terms out. Using the negative binomial theorem or the series expansion, here r is equal to q into e to the power t. On inputting the value into the formula, this gives us therefore, the MGF becomes Next, we have the hypergeometric distribution. For the hypergeometric distribution, an MGF is generally not used. This is because the summation becomes very lengthy and difficult to simplify. The PMF contains combinations in both the numerator and the denominator. So, standard theorems or expansions like binomial expansion, geometric series, exponential series, etc. can't be applied easily. Hence, the MGF for hypergeometric distribution is usually avoided. We move on to the last discrete distribution, that is the Poisson distribution. The MGF is We now apply the exponential series. Here, A is equal to lambda into t. This gives us Next, let's move on to the derivations of the MGFs for continuous distributions. We start with the uniform distribution. The MGF for this is given by integral from a to b exponent to the power tx times 1 upon b minus a dx. That is e to the power tx times the probability of the random variable x integrated over the range of x. This gives us the final MGF. Next, we move on to the gamma distribution. We start by writing the MGF as the integral from 0 to infinity exponent to the power dx times the probability of the random variable x under the gamma distribution. As we know, gamma of alpha upon lambda to the power alpha is equal to the integral from 0 to infinity x to the power alpha minus 1 times exponent to the power minus lambda times x dx. As we can see, the equation above follows the same form as this one does. Here, alpha is denoted as alpha itself, lambda is denoted as lambda minus t, as we can see clearly. So when we substitute this result in this equation, we get This gives us the final MGF as Now, let's move on to two special cases of the gamma distribution, the exponential distribution and the chi-square distribution. The exponential distribution is a special case of the gamma distribution with alpha equal to 1. Therefore, the MGF of the exponential distribution is obtained by putting alpha is equal to 1 in the MGF of the gamma distribution. Next, we have the chi-square distribution. This is the second special case of the gamma distribution with alpha equal to n by 2 and lambda equal to 1 upon 2. Therefore, the MGF of the chi-square distribution is obtained by putting alpha equal to n by 2 and lambda equal to 1 upon 2 in the MGF of the gamma distribution. These are the final MGFs obtained for the exponential and for the chi-square distribution respectively. Next, we have normal distribution. Next, we express x in the form of the standard normal variable z. We let z be equal to x minus mu upon sigma. This gives us x is equal to mu plus sigma z. When we differentiate this equation, we get dx is equal to sigma dz. Then we substitute these values. Now we're going to be using another substitution. For this, let u be equal to z minus t times sigma. This gives us z is equal to u plus t sigma. On differentiating, we obtain On solving this integral, we get the under root of 2 pi. From here, we get the final MGF. Let's talk about the remaining continuous distributions. For the log normal distribution, no finite closed form of the expression exists, as the MGF diverges at t greater than 0. Therefore, the MGF for this does not exist. Next, we have the t distribution and the f distribution. For the t distribution, the MGF doesn't exist at any point except at t is equal to 0. And for the f distribution, the MGF doesn't exist at all. For the beta distribution, the MGF does exist, but it involves special hypergeometric functions, which is far beyond the CS1 syllabus. Cumulant generating functions. A cumulant generating function is used to generate the cumulants of a random variable, such as the mean, variance, and skewness. This is represented using the Greek letter kappa. K1 is the first cumulant and it gives us the mean. K2 is the second cumulant and it gives us the variance. K3 is the third cumulant and it gives us the skewness. Therefore, cumulants provide another way of describing the distribution, just as moments do. The main advantage of cumulants is that many statistical results become simpler when written in terms of cumulants rather than moments. It is useful because it helps us to calculate cumulants easily, it helps us to find the mean and the variance in a simpler manner, and it simplifies many probability problems. The CGF, or the cumulant generating function of a random variable, is represented by and the formula to find this is simply the logarithm of the moment generating function. For the CGF to exist, the MGF must exist first. Let's understand this with the help of an example. The example states that the MGF of a binomial distribution is given. State the CGF of the distribution. To find the CGF, we simply take the logarithm of the MGF. Now, let's look at how to use the CGF to find cumulants. Once again, we have the same two methods, starting with the differentiation method. We find the CGF, differentiate it with respect to t. To find the kth cumulant, we differentiate k times. After differentiating, we put t is equal to 0. The value obtained is the kth cumulant. We already know that the CGF is given by the logarithm of MGF. Using this relationship, we will derive expressions for the first, second, and third cumulants in terms of the moments. We start by differentiating both sides with respect to t and put t is equal to 0. As we've covered earlier, the MGF at t is equal to 0 is given by 1. Therefore, we are left with this expression. We've also covered earlier that for the MGF, the expectation is found by taking the first derivative of the moment generating function with respect to t and putting t is equal to 0. Therefore, we use this substitution here. This gives us the first cumulant as expectation of x. For the second derivative, we differentiate the first derivative again. Then we put t is equal to 0. Again, the MGF at 0 becomes 1. This term becomes expectation of x whole square, and this term becomes expectation of x square, since we've differentiated it twice and put t is equal to 0. This gives us the second cumulant as ex square minus e of x whole square. This is also the formula for the variance. We repeat the process of differentiation once again to find the third derivative. Then we put 1 wherever necessary. This gives us the third cumulant as e of x cube minus 3 times e of x square e of x plus 2 times e of x whole cube. This is also the formula for skewness. Let's look at an example for this. The CGF is given by 4t plus 6t square plus 2t cube. Find the first and the second cumulants. As we know, the first cumulant is given by taking the first derivative of the CGF and putting t is equal to 0. For the second cumulant, we take the second derivative and then put t is equal to 0. Next, let's move on to the series expansion method. We start by finding the CGF. Then we expand it into powers of t, using whichever distribution is most appropriate in the question. We compare it with the standard expansion and find the cumulants by comparing the coefficients. We already know that the series expansion for the MGF is given by this expression. When we take logarithms, we get this expression. As we can observe, the coefficient of TR upon R factorial gives us the rth cumulant. Let's understand this with the help of an example. We start by using the exponential series. When we compare the coefficients, we get this gives us the value of all the cumulants. Now, let's cover the last topic for this chapter, linear functions. A linear function of a random variable x is a function of the form y is equal to a plus bx, where a and b are constants. This is useful because the MGF or the CGF of the new random variable y can be quickly found using the existing random variable x without starting from scratch. Suppose we're asked to derive the MGF of y. The standard form for the MGF of y is given by the expectation of e to the power ty. This can be written as expectation of e to the power t times a plus bx. As we can observe here, this again is the standard form of the MGF. This gives us Now again, using the same equation, let's derive the CGF of y. The CGF is given by the logarithm of the MGF. This can be expressed in the standard form of CGF. From here, we've derived the MGF and the CGF for the random variable y with respect to the random variable x. To conclude this topic, let's solve one numerical from each MGF and CGF. Starting with the first example, we have the moment generating function of x is given as exponent to the power 5t plus 3t square and y is equal to 2 plus 3x. Find the MGF for the random variable y. The MGF for y is given by e to the power at times m of bt with the subscript x. Substituting the values, we get Now we simply insert 3t in place of t. This gives us the final answer as e to the power 17t plus 27t square. In the second example, we've been given the CGF with respect to x and the equation for the random variable y. We are to find the CGF with respect to the random variable y. We start by writing the standard form. Then we insert 2t in place of t. This gives us the final CGF with respect to the random variable y. That brings us to the end of this week's video. I'll be back next week on Actuarial Simplified with Chapter 4 on joint distributions. See you next week.